In this lesson, we're going to take a look at something called the difference quotient. And the difference quotient is a very important tool for answering the question of finding a tangent line to a curve. In the last lesson, we talked about a secant line. This line right here is a secant line. Secant line touches a curve in 2 points. And we talked about the average rate of change, which is the slope of the secant line. And for this particular example, on this interval of 3 to 5, our secant line crosses through these 2 points here, and we end up with a slope of 2 for the secant line. Now the question is, what happens if we take these 2 points and we move them closer and closer together so that they become 1 point? What will the slope be? And that's when it becomes a tangent line. So what we want to say here is, if we have some beginning of our interval, call it A, and we have some x value here that's B, and this is our interval, and the distance between these, we're going to say the distance between these two numbers here, these two boundaries, is h. So we want to generalize this a little bit, and so let's call this x. And if we say this first point, instead of a, we say this is x, then the second point down here is going to be x plus h, because the h is the distance between the two endpoints. And if we put that into our formula for the average rate of change, delta y over delta x, we put the x plus h in for our first value, and we have f of x plus h minus f of x, and we have x plus h minus x. Again, that's just the average rate of change. Simplifying this here, we see that the x minus the x cancels out, and that leaves us with this formula right here, which we call the difference quotient. Now, to use the difference quotient, let's try it out here. Suppose we have a function here, f of x equals 2x plus 3. So our difference quotient says, we kind of call it d of x, and that's going to give us, we'll copy down, we had f of x plus h minus f of x all over h. Okay, now notice we don't have a specific interval because this is a general function for any interval. So let's substitute here. Now f of x plus h just means we're going to take x plus h and put it in the function. And when we put x plus h in this function, everywhere where there's an x, we're going to put x plus h. And so we have 2 times x plus h plus 3. So we've just substituted x plus h there, and I'm going to put parentheses around that because that's this first part. Now we have minus from right here, and so we got minus, and now we have f of x. Well, f of x is just this function right here, 2x plus 3. So I'm just going to copy that down, and parentheses are important here, 2x plus 3. And all that goes over h. So now it's just a matter of simplifying. So we're going to distribute this 2 here, and we have 2x plus 2h minus plus 3 minus, and actually we're going to distribute this minus sign here. So this thing's going to get distributed. We're going to minus 2x minus 3 all over h. Okay. With a little bit of simplifying now, we see the 2x cancels, 2x minus 2x, 3 minus 3 cancels, that's nice. And all we're left with is 2h over h, which is 2. And that's our difference quotient for this particular function. Okay. So for this function, the difference quotient is 2. So we can say d of x is 2. Now notice Here we have a function d of x, but there's no x over here. Well, this is because this is a simple linear function. So now let's look at a little more challenging one. We got a quadratic function here. So let's take d of x. Let's write down our formula first. Good place to start. F of x plus h minus f of x all over h. Now we're going to have to be careful here with our algebra. So we got x plus h, going to plug that in for x squared right here. And we're going to get, when we plug x plus h in, we get x plus h squared. Don't try to go too far too fast. That is our f of x plus h. So we've got the first part. Now let's write minus f of x. Well, f of x is just the function itself. So our function is x squared. So we have minus x squared. And again, I'm going to put in parentheses even though it's not going to change much here. You noticed here these parentheses are real important because we had two terms. And so we've got to watch out for that. So here, we just have one term. And bring across our h. Now we've got to square x plus h squared, and do this carefully. You can do it off to the side and remind yourself this comes out to be x squared plus 2xh plus h squared. And then we have our minus x here, minus x squared. So we'll copy that down all over h. And we see that the x squared minus x squared goes away. That's nice. So we end up with this equals 2xh plus h squared all over h. And we can cancel here. Since we have a binomial up top, we've got to cancel both an h from both terms, and we can do that. So we have 2x plus h. Okay, and so there's our difference quotient. So for this function, our difference quotient is for d of x equals 2x plus h. Now, let's keep in mind what we're talking about here. This is the rate of change for some interval from x to x plus h. So it's a generic formula for the rate of change on this interval. Well, we can use this now, since we have this magic formula for x squared. We have this magic formula. We can use it to find the rate of change for g of x equals x squared on 1, 3. Well, since we have the interval 1, 3, we can see that our x is just 1. So we have x equals 1. And x plus h equals 3. And h, remember, is just the distance between the two endpoints. So h is 3 minus 1, which is 2. Okay, from this 3 minus 1 here. Now, we have a value for x, we have a value for h for this interval. So if we want to find the difference quotient for this interval, we can say that this is d of x on this interval is 2 times 1 plus h is 2. So once again, we've taken this 1 and put it in for this x over here. We've taken this 2 and put it in for this h over here. And that gives us a value of 4. Okay, so again, that's telling us that this is the slope of the secant line. On the interval 1, 3 for this function. And finally, the last thing that we want to consider is what we call limit. And we want to see the limit as h goes to 0, because remember, we want to think about what happens here if we have this parabola for x squared. And we just looked at the interval from 1 to 3. And that line, that secant line, here had a slope of 4. Okay, and that's what we just found in the previous example there. And now the question is, what happens if we take this point and we drag it down here so that it's real close to this point, and so we end up with kind of 2 points that are real close, and eventually they just become 1 point. So what if we had an interval that had a distance of 0 or something very close to 0? Okay, and so if we think back to here, we had d of x, which we found in the last example for the function x squared. We had 2x plus h. Well, what happens as h goes to 0, as it gets really close to 0? Well, for this problem, we can say the limit, this is how we write it, as h goes to 0. So as h goes to 0, 2x plus h, well, it's pretty clear. If h was 0 or anything real close, then this is just worth 2x. All right? So that tells us when this distance is real small, then the slope of this line, we're still talking slope, the slope of this line here that touches in 1 point, this slope is going to be 2x. Well, this black line I have right here, which is intersecting at an x value of 1, we would have d of 1 equals 2 times 1, which is 2. So the slope of this black line would be 2 if these points were very, very, very close right here. Okay? So that's the difference quotient when we take h going to 0. And the key here is that the value of d of a, like we had d of 1 here, so in general, if it's d of a, the value of the d of a as h goes to 0 is the slope, still slope, of the line tangent to the curve a f of a. And this opens the door to the wonderful world of calculus, which we're not going to go into now, but there you have it. That's the difference quotient, which is a general form of the average rate of change.